Hello everyone, welcome to YouTube channel Energy-Exergy Theory Applications. I am Professor Morosuk and I am the author of this YouTube channel. Today we're with the topic exergy. All lectures have a very dynamic style of presentation. Definitely some of you would like to learn more, particularly about exergy. We will be happy to answer your questions and provide with an extended information. Our contact email you can find in the description of each video. Please support our work with a like to this video, subscribe the channel, and share the link with your colleagues. Our next lecture also dedicated to the exergy analysis of the energy conversion systems operate above the environmental temperature. We have quite a lot of such systems. All energy conversion systems, I mean all power plants, operate above the environmental temperature, and we need to find out something common rules that can be applied for exergy analysis of the entire system, and maybe something special depends on the system. Our previous lecture we discussed Rankine cycle. Does not matter steam cycle or organic Rankine cycle, exergy analysis of overall system will be the same. Now we will discuss in detail gas turbine systems. Actually, more complex systems, open cycle gas turbine systems. Open cycle gas turbine systems, the simple, consists of three components: air and expander. Sometimes call it gas turbine, but not gas system. This you should clearly distinguish. Gas turbine system, it is entire system, and today we will discuss about entire system, but not one component. According to energy analysis, energy efficiency, it is positive effect over supplied energy in order to achieve this effect. Therefore, positive effect, it is W net of the system, which is work of expander minus work of air compressor. So this is our positive effect. And heat supply to the system is expressed in the terms of mass flow rate of fuel, and lower heating value or higher heating value of fuel depends which rules we would like to apply, because lower heating value is a very common variable for European thermodynamic school, and higher heating value quite often applied in US, in Japan. So we need to very carefully observe publications. Applied lower heating value or higher heating value does not matter. So this is energetic analysis. Now let us proceed with exergetic analysis. Let us repeat exergy balance of the entire system. Exergy of fuel is equal exergy of product plus exergy destruction within the system. So it means sum of exergy destruction within each component and exergy losses, and exergetic efficiency product over fuel. For open cycle gas turbine system, at least for the simple that we're discussing now, all components are productive. So fuel of the system, it is exergy of the air and exergy of fuel. Product of the system, it is W net, work of expander minus work of compressor. Losses of the system associated with stream 5, it is exergy of combustion gases, and exergy destruction of the system, it is exergy destruction within three components: air compressor, combustion chamber, and expander. For the exergy analysis, we always should discuss state zero. We know that the first topic to discuss for the application of exergy analysis, where to select state zero. For open cycle gas turbine system, it is quite obvious this answer, because air is coming from the environment. Definitely temperature and pressure of air coming from the environment will be state zero for exergy analysis. And we also know how many working fluids, so many states zero. So it means that temperature and pressure will be the same, and enthalpy and entropy to calculate physical exergy will depend on the properties of working fluids. For open cycle gas turbine system, we have three working fluids: air, which is compressed within air compressor, so it is one working fluid. Another working fluid, it is fuel. that is coming to combustion chamber. And third working fluid, it is combustion gases expanded within the expander. So it means that in order to start with the exergy analysis of the open cycle gas turbine system, we need to proceed with three-state theorem for each working fluid that involved in this energy conversion system. So one more time, product of the system, it is W net that will be charged to the grid if it is electricity, or for work that can be used for other energy conversion system. And very interesting observation associated with the losses of the system. If we will discuss exergy as exergy of stream as sum of physical and chemical exergy, we can observe that for stream 5, physical exergy dominates and chemical exergy is a very low value. Absolutely the same can be observed for state 4. After the combustion chamber, we have very high physical exergy and chemical exergy low value, and chemical exergy at state 4 and 5 are the same. So now a few words about air. Air is coming, as we already mentioned, directly from the environment. That's why it is state 0 for the exergy analysis. But air can be simulated differently. If we have software, good software, then we will immediately simulate entire system under assumption that air is real. So it means that air will consist of all gases that usually form air, and also humidity will be included. Or if it is simple calculations, or maybe even head-made calculations, then we definitely will assume that air is dry, no humidity, or even we can assume that it is theoretical air, means only nitrogen and oxygen, two gases that are formed air. So now for us, very important, humidity is included to air or not included. So physical exergy of air, regardless if air is assumed to be real or air assumed to be theoretical or dry, physical exergy will be 0 because air is coming directly from the environment. And chemical exergy also will be 0 if humidity is not included, not considered. But at this point, I would like to bring your attention. For the fuel, never write that fuel is only exergy of fuel, but anyway, E1, so exergy of air is 0, therefore no need to write in the balance. This is a mistake. You always should write that fuel of the entire system, it is real fuel and air, and in case if exergy of air is 0, it will be 0. But within balance, this value, this term, always should be mentioned. Otherwise, it can be the problems with the calculations. Now we will discuss another possibility of operation possibility of open cycle gas turbine system. For example, multi-fuel gas turbine system. At present, there is a modern research which is called multi-fuel systems. So using open cycle gas turbine system, we will find what means multi-fuel system and how it should be considered. So multi-fuel system for us, for open cycle gas turbine system, means that two fuels will be combusted together. Practical example is, it is modern research, when hydrogen is added to the combustion process in addition to natural gas or to methane. It's called combustion of hydrogen blends. Quite a lot of companies are working with this approach, and they're discussing the evaluation of system, operation parameters, and so on. So it means that it is absolute realistic idea and practical task. If we proceed with energy analysis, then two fuels should be considered as the energy supplied to the system. We need to simulate a system, and we need to find out mass flow rate of one fuel, mass flow rate of another fuel, and corresponding lower heating value or higher heating value depends on what we will use for analysis. And this is approach, when two fuels burn together within combustion chamber, call it co-firing. Also, co-firing, for example, for steam power plants, it can be biomass and coal. But but definitely not for gas turbine system. I'm discussing about steam power plant. So by co-firing effect of co-firing and approach of co-firing, it is multi-fuel systems. And now you can see how to consider that. For exergy analysis, we also should some exergy of fuel A and exergy of fuel B. It will be within the term of exergy fuel of the overall system. There is approach multi-fuel systems, but with a little bit different arrangement. So we have open cycle gas turbine system, and now we will preheat air after air compressor before combustion chamber, for example, using solar energy. Such a research also. Then for energy analysis, we will add the heat that is coming from solar energy. But since we have two fuels used not for the same component in different component, this will be already multi-fuel. So it is not co-firing because solar energy, of course, we cannot co-fire. It is multi-fuel effect. We have one component and another component where energy is applied to the system, and it will be expressed like that. And for the exergetic analysis, also effect of second fuel, so means solar energy, will be included. Here I use it intermediate transfer of solar energy to the system with stream 8, stream 9, because directly solar energy definitely will be not used for the heat exchanger within open cycle gas turbine system. But depends on the situation, you need to check the system, and if there is another fuel, it should be added as a fuel of the overall system, in not only in energy analysis but also in exergy analysis. And definitely within exergy analysis, we will have more proper results how adding of additional fuel for co-firing or for multi-fuel, how it will affect to the increasing of efficiency of the overall system or decreasing the use of fossil fuels. The concept, which is called combined cycle. Definitely, many of you know this concept, but very briefly, I will repeat. We know that for open cycle gas turbine system, exergy losses associated with stream 5. And physical exergy dominate, and chemical exergy is not a high value. And definitely we need to develop idea how to reduce losses, so how to decrease physical exergy at stream 5. Within the system, open gas turbine system, it's difficult to do it, but we can use this heat, or better to say physical exergy, for another energy conversion system. And what it means, we can use combustion gases, very high temperature combustion gases, for heat recovery steam generator, which is part of Rankine cycle. It can be organic Rankine cycle, or it can be steam power plant. Here we will discuss this simple schematic, because again, for us it's very important to discuss concept but not discuss particular evaluation of Rankine cycle. So which benefit it will bring us? Fuel supplied will be the same. Stream 5, it is utilization of heat within the system, and we will add, in addition to the work produced by gas turbine system, we will also add work produced by steam power plant. And we should remember that since it is new kind of energy conversion system, which is called combined cycle, the boundary condition will include both systems together, open cycle gas turbine system and Rankine cycle. So combined cycle, we cannot evaluate part by part. We need to evaluate everything together as a new kind of complex energy conversion system. And exergy analysis of combined cycle. As usual, we will start with the state 0, and state 0 always will be associated with air coming from the environment. Here we will have state 0 for air, for fuel, for combustion gases, and of course for water, because or for, if it is organic Rankine cycle, for the working fluid, which is inside of organic Rankine cycle, and for also for cooling media, for water or for air, depends on how condenser will be cooled. So fuel of the system, we already mentioned, so balance, products plus destruction plus losses of the system. Fuel of the system, it is the same as for cycle gas turbine system, exergy-1, exergy-3, exergy rate, of course, and product of the system, W net, it is W net coming from gas turbine system and from steam power plant. Interesting is to discuss losses of combined cycle. If we assume that all components are productive, then losses will be stream 15. It is combustion gases that will go to the environment. It is exergy transfer to the environment, plus the difference between 14 and 13. So cooling water for condenser, in case if condenser is considered as productive component. But very often for the combined cycle power plant, we can consider condenser is dissipative component, then streams 13, 14 will be not included, and a condenser will be treated as a dissipative component. So means exergy destruction will be a little bit higher because losses will be lower. But this we discussed in the previous lecture. Our next lecture, we will continue again with the system operates above the environmental temperature, but our topic will be chemical systems with energy intensive processes. If you found this video is interesting and useful, please support us with your likes, comments for this video, give your feedback, please subscribe the channel and share the link with your colleagues. Thank you.